All right, yes, so I'm here today to talk to you about the Erlang Scheduler, because I don't know about you, but at least for me, I use processes and everything, but I've never really thought about how this works, because it just works. But I like knowing how things work, at least a little bit. So first, most important thing, God, why is it not working again? Oh, there we are. This is my cat. He's really cute. It's just there to get you all feeling positive about this talk, like you're a little cat in the sunshine. But anyway, the scheduler is one of the core parts of the beam that make it so powerful, right? So the point of this talk, it's not to be 10 out of 10, 100% nitty-gritty details correct on the actual implementation. It's more to help you build a mental model of how it works. So if you know nothing about the scheduler, you get a basic idea, and then tomorrow you can go into the nitty-gritty and how you can actually mess with it. Because honestly, most of us, we don't need to mess with it. But I think tomorrow, Robin will be talking about that. All right, so we're going to start in a very, very simple world. We have one core, we have one scheduler. Right? So in this world, we're not actually talking about parallelism, because parallelism means that you're actually doing multiple things at the same time. And if you have multiple cores and multiple schedulers, then you can do that. But in this simple world that we're starting in, what we're really doing is concurrency, which is making progress on a lot of things by doing little chunks of work in a row. So it looks like you're doing a lot of things at the same time, but really we're switching tasks very, very quickly. And as I was writing this talk for the longest time, until literally a day before the first time I gave it, I had only one slide. And it just said this, taking turns. Because if you remember nothing else, that is what the scheduler does. It helps the processes decide whose turn it is next. And there's two types of scheduling here that help you determine how to take turns. Cooperative scheduling and preemptive scheduling. And to understand the difference between these two, if you're an only child, this analogy might not land, but imagine you and your siblings are playing video games. If there's a cooperative scheduler, you have to rely on the other process, the thing that is doing the work, your little brother that's playing the video game, they have to cooperate with you. They have to yield and say, okay, it's fine, I'm done, it's your turn now. But as you can imagine, that doesn't always work if somebody is hogging the resources. Or in this case, if your sibling doesn't want to give up the controller. And that is where preemptive scheduling comes in. This is where something else, the scheduler in the Erlang case, your mom in this analogy, is in charge. So in this, I'm playing this video. I was the oldest sibling, so I never had this problem because, I did not cooperate. And what are they going to do about it? They're little. But in this case, your mom says, hey, you've been playing for a while. Let your sibling go. Take a turn. Or, you each get to play until you die, and then the next one goes. And that is kind of what the Erlang scheduler does. It's a kind of a combination because the processes do have to cooperate, right? They can't just get cut off in the middle of doing something. They have to stop at an available point. But in principle, the scheduler is in charge of who gets a turn and how long your turn lasts. So each process gets about 4,000 reductions, which is like a unit of work, before the next process goes. So I feel like we hear the word reductions a lot, and I still find it kind of hard to, what is a reduction? Why do we call it reductions? So for all intents and purposes, you can think of it as a function call. And it comes from the prologue history, the prologue roots of Erlang, where you'd use, take a step to reduce, the logical problem, to a next state, next state, next state. And that's why it's called why we call it reductions. So each process gets 4,000 reductions before it has to wait again. And to me, I find it incomprehensible, how fast that is, right? This one process can do 4,000 things. I do 5 things on a good day, and it takes microseconds, nanoseconds to do these 4,000 things. So to see how the scheduler does all this, we have to have a look at the different states that a process can be in. So a single process can be in various states. There's a few other ones, but the simplest one is you're running, which means it's currently your turn, you are doing things, you're calling functions, doing whatever. And then you have two options. Either you're done because you have no more messages, like maybe you only did 3,000 things, but you don't have any more things to do. Then the process goes into a waiting state. And if a new message comes in, it goes back into the queue, and it's like, hey, okay, I have work to do again now. I'd like another turn. The other option is that you actually have a lot of work to do, so you've done your 4,000 reductions, but so you're done, somebody else gets a turn, and then you go into the runnable state. And the scheduler always picks processes that are in a runnable state. There's some other states, like garbage collecting, exiting, suspended, but for the sake of this talk, we're not going to worry about those. Some of them speak for themselves, like exiting, garbage collecting, but yeah, that's... And then there's a last option, and that is a timeout. So if a process is in the waiting state, and no message comes in for however much, like 5 seconds, 10 seconds, then it gets a timeout message, and it goes back into runnable to handle the timeout. So this is also why Erlang doesn't guarantee that your timeout will trigger after exactly 5 seconds. Because what really happens is after 5 seconds, it goes back into the queue to handle the timeout when it is its turn. So it means that it could take a little bit longer for the timeout to actually get handled, depending on how long the queue is. So in this world, we thought, okay, there's one queue, the scheduler picks the next one, but it's a little more complicated than that. There are actually 3 queues. We have max priority, high priority, and normal and low go together. So you can change the priority of a process. I'd say probably don't do it, although I'm sure in tomorrow's talk, where we are messing with the scheduler, he'll tell you to do it, I don't know. But yeah. So max priority is Erlang internal only, and I've been trying to figure out exactly if there's any examples of this. The best I got yesterday from Francesco was something related to tracing. So if there's anybody in the audience who does have a good example of like how Erlang internals do use max priority, please use some of the question time to preemptively answer that question, because I know I'll get it. So max is blocking, right? Like if something comes in with max priority, we do nothing else until the max priority queue is empty. And then the same goes for the high priority. We do nothing else until the high priority queue is empty. Normal and low are a little bit different. So you can see my beautiful snail right there. That's a low priority task. So what happens with the low priority tasks is that those go through the queue 7 times before they get picked up. So normal priority tasks, they don't block the low ones. It just takes longer for the low priority processes to get picked up. So that's really the basics. So, but obviously we have to do other things. Sometimes we have to interface with the outside world, outside of the beam. Things like reading a file, loading some data, etc. And that's where ports come in. So we communicate with the outside world via ports, and ports also get a turn before the next process gets picked. And ports also get 4,000 reductions, but since we're not neatly in like Erlang world here, we don't really have reductions, so instead, each task is counts as a certain number of reductions. So for example, each task is worth about 200 reductions, plus some more based on like the byte size of the data that you're reading. Yeah. So things like opening a port, closing a port, sending, receiving data, those will take up a certain number of reductions before the port tasks are done, and we go on to the next thing. Ports generally get to go before the next process is picked. So this is kind of how it works if you have only one scheduler. So we're going to zoom out a little bit, and we're going to say, like, okay, but I live in the modern world. My computer has more than one CPU core. I can have multiple schedulers, and I can have real parallelism. So if everything is perfectly balanced, right, then all your schedulers are roughly equally busy. But sometimes more work comes in to one node, then another, or one core, then another. And that is where the schedulers collaborate to make sure they're all evenly busy. One of the ways they do that is by task stealing. This is really fast, so this happens every cycle, right? Like, oh, do I have any tasks? No, I don't. Okay, so as you can see, your scheduler number 1 is idle. It has nothing to do. So what it does, it goes in order. In a world where like all the schedulers are numbers, right? We're going in order, and we're going to take the highest priority task from the first scheduler that we encounter that has anything to do. So we don't care about the highest priority task, just the first task that is stealable. So in this case, the task that's going to get taken is the normal priority, the little b, from the second scheduler. Even though there is a higher priority task on scheduler number 3, we don't even get there because we go in order. And this is the quick and dirty, simple way of balancing the load between schedulers. But then every once in a while, every 2,000 scheduler turns, we do a little bit more work to make sure that it really evens out. So what we do is we check for each scheduler. We now have 4 because that worked better for the graph than 3. It doesn't matter. So in this case, we count how long the average max queue length is for each scheduler, like how many tasks are waiting, how many processes are waiting to run. And we set up a migration. So as you can see, the average is 2.5. On average, we have 2.5 processes per scheduler. But as you can see, scheduler 3 has nothing to do, and scheduler 1 is really busy. And then 2 and 4, like 2 is not that busy, 4 is a little bit busy, but the difference isn't that big. So what we do is we order the schedulers from least busy to busiest, and the extremes are going to migrate to each other. So we say, okay, scheduler 1, you should send some work to scheduler 3. Scheduler 3, you should take some work from scheduler 1, and then 2 and 4. So we set up this migration path. We recalculate this balance every 2,000 scheduler turns. And then for those next 2,001, every time, so the next time scheduler 3 has to pick a process, it'll go like, oh, where should I take it from? Oh, I should take it from 1. But only if we're still unbalanced. So if after a few rounds, scheduler 3 now is busy and suddenly has 3 things in the queue, it will not steal because it's already above the average. And that kind of ensures that in an ideal world, all your schedulers are roughly equally busy. Because that's how you achieve like the optimal parallelism, right? If every single scheduler at every core is doing the most amount of work that it can. So that kind of is, I'm not going to say that's all there's to it, but if you're just thinking about like conceptually, that's kind of what all that's to it. So to summarize, first we update our reduction counters. So we go like, okay, this is how many tasks you've had, etc. Then we check all the timers to see do any timeouts have to trigger, etc. And then we do this balance check in the migrations, but only every 2,000 turns. Then we do any port tasks, and only then do we pick the next process. And for some reason, I'm talking much faster today than I have before. But that's okay, because that means I can do my extra slide, which is that even though this is all nice, but this is nice if you live in Erlang world, right, where you have reductions, and your processes do generally tend to cooperate. But if you want to write NIFs and other dangerous things, right, then you can get in trouble. Because what if something is hogging everything outside of the beam and the scheduler doesn't quite have that much power? And that is where dirty schedulers come in. This was actually my second slide for the longest time. And I was like, what if all else fails, I'll just put a little picture of Christina Aguilera in there. But then I finished the rest of the slides and I forgot about Christina Aguilera until every time I'm on stage, I'm like, oh shit, I should have put in the picture of Christina Aguilera. If I do this talk another time, she'll be there. But anyway, so dirty schedulers are schedulers specifically for work that happens outside the beam. Less neat, less tidy, CPU heavy, IO heavy, and they run in a separate thread. So they can kind of like, they ensure that you can do all this like dangerous outside of the beam CPU heavy work without it completely blocking all the resources from from everything else that is running in the beam. And generally speaking, you have the same number of regular schedulers as you have dirty schedulers. But yeah, and you can have a lot of schedulers. I forgot the exact number, but you can have theoretically you could have thousands and thousands of schedulers, but most of the time you'll have one per CPU core, because if you have more, you can't, like, they don't really do more parallel work anyway. So yeah, if you want to know more about this, you can read the Beam book, and get it signed, I saw actually, right? I saw a little table that you can get your Beam book signed if you have it. You can read the Erlang documentation. If people still do that these days, I guess you could ask ChatGPT. I don't know if it'll do you much good. Yeah, I used a blog post from the AppSignal folks about a deep dive into Erlang Scheduler. And tomorrow, there will be a talk. Now you have kind of an understanding how it works, and then tomorrow you can see how you can really dive in. And then, because I didn't want him to feel left out, a picture of my other cats. All right, thank you very much. So yeah, I guess I have a question for the audience. Other than tracing, does anybody know of any like max priority things in Erlang? What that would be used for? Maybe the people who know aren't in the audience.
There's somebody.
Yeah?
The code server, you think? Oh. You're guessing, or you saw that?
Oh, you're guessing. Maybe, I don't know, yeah.
We actually have an online question here. 1 second, I'm going to come to you. Oh, 1 second. How do the different schedulers communicate with each other? Ivano Pagano was asking.
That's a very good question. I'm actually not sure how they really talk to each other. I mean, I want to say they pass messages, probably, but I don't actually know. I'm not sure. I don't know if anybody in the audience knows. It's my tactic. If I don't know, there's probably people in the audience who know more than me about all of this, so.